Welcome to AirSpace from the Smithsonian's National Air and Space Museum. I'm Emily.
And I'm Matt. In the 1950s and 60s, the space race was on between the Americans and the Soviets. Who would send a man to the moon first? At the same time, the US and the USSR were also locked in a Cold War battle for intelligence.
The space race and the Cold War were inextricably linked. Some of the first satellites we put into space were spy satellites. These eyes in the sky looked for missiles and bombers. They listened for radar signals, and they kept an eye on our adversaries.
Today, we're taking a look and a listen to how two of these spy satellites worked. That's on AirSpace, sponsored by Lockheed Martin.
Matt, we spend a lot of time on our phones. I spend a lot of time on my phone. I'm pretty sure you do too. And I think that we spend so much time thinking about which apps we don't want tracking our locations and which apps we need tracking our locations so that we know how to navigate, that we forget what it was like in the 50s and 60s and how far we've come.
And the reason we're able to take it for granted, right, is because that infrastructure has been so built up over these past decades since the beginning of the space age, to where now we are using all of these space-enabled apps and technologies without even thinking that when we're using them, these things are actually bouncing around off of satellites in space and then, come down to us via, cell phone towers and other things. But yeah, there was a time when this was all brand new.
And I think I forget all the time. In the 50s and 60s, we're already deep into this space race, and it's really easy for me to forget that we're still kind of in film camera mode. We're still pretty analog with so many of our technologies.
That's right. You have essentially two technologies for capturing images. One of them is the sort of analog method of, film and traditional cameras with lenses and shutters and all of that. And then you have television cameras that can send an electronic signal, but are a lot less high res than an actual image snapped with a camera.
Right. And so a lot of the stuff that we take for granted on a daily basis, because it's such a foundational part of how our lives work now, really you can start to point back to the really rapid development of these technologies for intelligence work, which means all of the satellite-based technologies that we're using today are born during this point in time when satellites were being developed as part of the Cold War.
Yeah, so obviously, right, war and intelligence gathering, none of that stuff is new. People had been trying to gather intelligence in previous eras of conflict, but now we're entering into this post-World War II era that's sort of an era of high technology. We're going to see things like the space race, which is based on the development of new missile technologies, and then we're also going to see new satellites that will become the basis of our communications networks today, but were originally intended for intelligence gatherings between two very powerful global superpowers who are also trying to outpace each other in the development of new military technologies.
So what do we do, Matt, when we want to learn more?
Well, we always go to the experts. So we talked to Keith Masback.
Yes, my name is Keith Masback. I've spent 30 plus years between being a uniformed Army officer and a senior executive civilian in the Department of Defense and the intelligence community, the vast majority of which was working on remote sensing and the integration of intelligence, surveillance, and reconnaissance. So we came out of World War II, and there was a new world order necessarily. And the tensions had been brewing and immediately began to grow between sort of the West and the East. And that tension was fueled by the race to acquire ballistic missiles and nuclear capability, which obviously we, the U.S., had demonstrated. And that immediately created an intelligence need, an ongoing intelligence need to be able to understand and characterize what our adversaries were doing. What progress were they making? How were they deploying things? How did they plan to employ things?
There were also internal tensions in America. From 1950, American troops were on the ground in Korea. And by 1953, the new Eisenhower administration was looking for ways to prevent wars before they started and keep the cost of war lower in money and in lives.
To do that, you really needed your own nuclear capabilities, of course, but you also needed knowledge of what your adversary is doing. And in terms of trying to put together the intelligence that would tell us how many missiles the Soviet Union had and how many facilities they had producing them, estimates based on traditional intelligence gathering techniques varied.
So the Eisenhower administration hoped to take a different policy than the Truman administration in terms of how to go about waging the Cold War.
That's Andrew Ross.
My name is Andrew Ross. I am a 6-year PhD candidate at Georgetown University. I am also a Guggenheim Fellow at the National Air and Space Museum. As they saw it, the Truman administration was trying to put out fires wherever the Soviet Union was setting them up. In this case, Korea. They wanted to not necessarily fight troops with troops, but they approached the Cold War from a much more nuclear-oriented perspective by threatening large-scale nuclear attack in the event that something like the European landmass were to be invaded. So don't invade West Germany, because if you do, we will respond with nuclear weapons. What became crucial is intelligence operations. We need to understand the degree to which the Soviet Union has nuclear capabilities in the form of actual weapons or vehicles that could transport those weapons to various parts of Europe or even the United States.
The military branches knew that Eisenhower's goals was to spend less money on the military, and each branch of the military didn't want to get their budget slashed. This is what you do when you feel like your budget's in jeopardy. You work really hard to make sure people know what it is that you can provide.
And so the various branches of the military started to develop their own intelligence estimates of what nuclear capabilities the Soviet Union had. And those estimates often reflected the degree of how advantageous it would be for that branch. Specifically, there is a part of the Air Force called the Strategic Air Command that basically oversaw, if a nuclear war were to break out, they would be the part of the Air Force that would deliver nuclear weapons to their target sites in the Soviet Union. And their intelligence estimates were often, what we now know, widely exaggerated and based off of very little evidence. But if the Soviet Union had all these targets to destroy, then their budgets relative to the other budgets of the military would grow.
But regardless of whether the Soviet Union had a lot of nuclear capability or just a little, the US really wanted to know what it was and put the smallest error bars possible on that number.
There's something called the bomber gap and the missile gap. The bomber gap arose in 1954, 1955. It was based off of a fear that the Soviet Union actually had significant long-range bomber capabilities, potentially surpassing that of the United States. And then the missile gap developed around 1957, 58, around the time of Sputnik and thereafter. And the worry was that not only could the U.S. be behind in developing long-range bombers, but that they could also be behind in developing long-range missiles. And I think the fear was that if either or both of these were the case, the U.S. nuclear deterrent would not be as effective because potentially the Soviet Union could launch a surprise first strike, take out the ability to the United States to then respond.
And the first program that ended up trying to get the answer to how many missiles and bombers did the Soviet Union actually have was the high-altitude flyovers of the U-2 aircraft.
I'm certain that we could do an entire episode on the development and deployment and the use of the U-2, which is definitely not what we're doing today. And frankly, Matt, let's be honest, I'm sure there's dissertations, books, documentaries. There's all kinds of things to say about the U-2. No,
there's even a band named after
even a
this
band.
airplane. Come on.
Right? And actually, Matt, do you remember in the OG AirSpace days, we did an episode called Spies in the Sky, where we talked about spying from hot air balloons and the development of the U-2 and the SR-71.
That's right.
And we're not doing that today.
No.
However, The U-2 was a state-of-the-art high-altitude jet that was equipped with one really special camera. The U-2 spy plane is something that a lot of folks know and have heard about and was really the thing that revolutionized the ability to spy from the air.
Yeah, and just to describe it a little bit to listeners if they haven't seen the U-2, it is a small plane, has one seat, so the pilot was also the navigator and the photographer, and by all accounts, this was pretty much a difficult job, or a difficult 3 or 4 jobs for one person to do all at once while flying over enemy airspace.
We developed the U-2 program very rapidly, this high altitude reconnaissance platform, which when it was birthed was untouchable by our adversaries. But we knew that that opportunity was waning, and we had to understand how to get to yet higher ground.
The opportunity to do high-altitude aerial reconnaissance without our adversaries knowing we were up there was really short-lived, Matt.
Yeah. In May of 1960, only 4 years after the first U-2 flight, the Soviets shot down a U-2 flown by a CIA pilot named Gary Powers, who was able to eject from the airplane, but was captured along with the aircraft and its camera.
At first, the United States claims that this flight was actually a totally scientific flight. It was a NASA flight to observe data related to upper atmospheric weather. And after the United States made this announcement, the Soviet Union came out and said, well, we have the pilot's papers here that show he is an intelligence agent, and that we have, the reconnaissance camera, we have his logs on where he is flying to. This was against international law.
So no matter how high you're flying in an enemy's airspace, doing that without their permission is illegal, and it's violating that airspace. But space is a different story.
Orbital flight paths over crossing countries became a norm and a custom that most countries accepted as something that if you can access outer space, then you have freedom of action in outer space.
The Soviets got to space first with their satellite Sputnik, which some consider to be a failure by the United States in the space race. But it turns out that Sputnik being launched by the Soviets may have actually helped the legality and the general acceptance of U.S. satellites in space.
Actually, in an ironic way, it was very useful for the Eisenhower administration that Sputnik was launched before any U.S. satellite was, because there was a lot of worry in the Eisenhower administration of whether countries were going to go to the United Nations and complain that these U.S.-based satellites were interfering with the sovereign airspace of a country it was passing over. But the Eisenhower administration was actually somewhat, I wouldn't say relieved, but it did work out in their favor that the launch of Sputnik contributed to this freedom of action in outer space that they then planned on taking advantage of with their own reconnaissance satellites in the coming years.
So the U.S. had the U-2 flyovers, and we also had intelligence being gathered from just outside of the borders of Soviet territory. But this didn't really get you into the interior of Russia, which is a pretty big interior. Russia is a very large country. And so what they really needed was to get to the highest ground possible.
And by ground, you mean space.
That's right.
Where there is no ground.
No, metaphorical ground.
Metaphorical ground. Cool. So we're going to talk about what the United States did finally get into space with its own space satellites, which is wrapped up into a satellite program called Corona. But before Corona happened, the very first set of spy satellites that the United States sent to space were not imaging satellites, but they were listening satellites.
Grab was actually just ahead of the Corona program, but almost no one's ever heard of it. And the idea was that being able to see, characterize, and understand radar activity, largely, in the Soviet Union was critically important. So heretofore, again, we were only able to do that with aircraft. Those aircraft flew along, hugged the coast, just phenomenal, heroic stories of the crews that did both imaging and signals intelligence collection from aircraft during the Cold War that most people don't know about. Many lives lost in that courageous service. Just like being able to use Corona to get into and over Soviet airspace without being able to be held at risk. Grab provided that same thing for ELINT. So I could maybe aircraft could get up to 200 miles inland. Soviet Union, now Russia, pretty big expanse. So the ability to see that from space, again, to detect, characterize, and then begin to understand the signals intelligence, the electronic intelligence activity was critically important to pursuing our Cold War intelligence requirements.
So Keith just used the acronym ELINT, which stands for Electronic Intelligence. Grab wasn't listening for things like conversations. It was listening for things like radar, electronic signals.
And GRAB, Matt, GRAB is also an acronym, right?
Yeah, that's right. GRAB was also an acronym. It's not grabbing things, although, it is kind of grabbing the radar, if you will. It's the Galactic Radiation and Background Satellite, which is, a little bit of a misleading name because you don't want to say that you're launching a spy satellite and call it a spy satellite or anything that indicates spy satellite. So you pretend that you're actually looking for this sort of background signals of the galaxy. And in fact, GRAB wasn't even the name that most people knew this satellite by. Publicly, it was called SOLRAD. And the idea was this was going to be studying solar radiation, right? Not listening to the radar stations of the Soviet Union and its allies.
The thing about a lot of these systems is they are multifunctional in that they can do reconnaissance tasks, but they can also record data that would be useful for scientists. And often it's not a one or the other, but the ability to do both at the same time was actually utilized by the military so that they could kind of have this cover of a scientific, nominally peaceful initiative where maybe they were doing some of those tasks, but maybe they were also, as in the case of GRAB, monitoring radar systems in the Soviet Union to locate where these radars were that were used in air defense systems so that like if a U.S. bomber were to enter Soviet airspace, it would know where to fly so that it would not be detected by Soviet air defense systems and shot down. So it could reach its target before the Soviet Union could respond. But at the same time, the GRAB satellite could also monitor solar ray activity up in Earth orbit and monitor the degree to which solar rays could potentially interfere with a satellite communication network.
That also was important with respect to operations, with respect to the B-52, right? So you've got to know where you can and can't fly. Where are the gaps? They can't possibly have air defenses and radars that can see everywhere, that can overlap all over the country, all around their important areas. So when you can begin to map that and understand that in great detail, then that tells your B-52 pilots exactly where they can fly to have penetration into the Soviet Union.
And Matt, part of this story is a lot easier to understand when we kind of recognize that radar is newer technology at this point in history.
Yeah, if you think about radar as a technology, it is very new. It was developed just in sort of the lead up to World War II and then really got accelerated in its development during the war because it was incredibly useful in wartime for, detecting things flying over you, et cetera. So, now everybody suddenly has radar bases, and these are incredibly useful. They are the sort of new big military technology. Aside from the weapons that come out of the war, radar is the other sort of new big technology coming out of this.
And GRAB really helped revolutionize how U.S. intelligence agencies were gathering information and making recommendations because it was adding this sort of, let's call it a bird's eye view perspective to gathering intelligence rather than just doing it from the ground. But the GRAB satellites also did a lot in terms of advancing technology so that we could start the development of technologies like imaging from space.
A lot of the technologies that were used in these first spy satellites, we started applying them to other forms of satellites and to interplanetary missions, lunar missions, et cetera. Like, for example, there is no such thing yet as like a computer hard drive in the 1950s and 60s. It's all magnetic tape. So you're developing magnetic tape systems that can be sent into space that will record data when you want them to and then will replay that data and send it back to you when you want them to. So developing those systems is pretty key to what happens with later missions as they're sort of building more and more capable satellites and probes.
So just as Grab started off as the precursor that laid the foundation to the Corona system of satellites that were able to actually take images, it took a lot of failures before a successful Corona satellite was able to produce photos, which I don't think this should be a surprise to anybody. You keep testing and developing and changing until the thing works. But Matt, before Corona really started taking pictures, it was actually doing science before it was doing intelligence, right?
Yeah, there were several sort of test missions that had to happen before Corona could fly successfully.
It did not succeed for various reasons from launch on for the first 12 missions, and only was able to return a test canister that was caught in the air from space. On the 13th mission, the cover story, of course, was it was called Discoverer. So on Discoverer 14 was the first time that they were able to capture imagery, return the canister, catch the canister in the air, then develop that film and deliver it to imagery analysts.
In the early years of developing Corona, it sort of had a scientific cover, and there were scientists attaching instruments to it and doing mostly sort of geophysical research with it. And Ed Stone, who later became famous as instrumental member of the Voyager team that sent the 2 Voyager spacecraft out into space, he actually got his start as a space scientist attaching instruments and doing experiments with Discoverer, kind of, as we said, providing scientific cover for what was otherwise a spy program, but also that scientific cover was real scientists doing real science.
The Yankee in me loves that not a moment was wasted. We were either getting intelligence or science out of this thing. Makes me so happy. The thriftiness, I tell you what.
Yeah, nothing's wasted.
Nothing wasted. And I think, Matt, this is a really good moment to sort of talk a little bit about the progression of things, right? Corona is taking photos on film. And this is a stepping stone to a program that is in development at the exact same time, which is to do this digitally.
At the same time that the Corona satellite program was being developed, there was multiple other reconnaissance satellite programs under development as well. Another is called SAMOS. And the idea was to use electronic information that was basically beamed down to tracking stations from a reconnaissance satellite in orbit. And Corona was seen as basically a stopgap in between the ending of U-2 aircraft reconnaissance and SAMOS. But the thing is, electronic transfer of satellite reconnaissance photography was not high resolution enough at the time. And so the Corona program was only supposed to last a couple of years while SAMOS was developed, but Corona technology only increased, even though it had like its analog limitations. And so what initially was seen as a rather rudimentary system actually became, one, relatively affordable, but two, actually quite effective for the next 10 years.
So it sounds like, based off of the work that was developed for the U-2 plane, we're really good at photography. We got this. We figured out how to make really good cameras and put them on airplanes and get really high resolution, really valuable intelligence from a plane. But taking that to space, film cameras, and all of that, how do we get a satellite with photography film inside of it back down here on Earth? And how do we do all of that using Corona as the stepping stone to the development of the technology of the SAMOS?
Yeah, I mean, unfortunately, you can't just use the type of film that you would pop into your camera if you had a film camera, right? That stuff's made of cellulose acetate, and that gets really brittle in the cold, and it gets pretty cold in space, when you don't have the sun shining on you anyway. And so they had to develop a new type of film that would not get brittle, but it would stay, pliable. And so what they ended up using was a type of polyester to make a new type of space film.
Can we also just pause here for a moment and say, you and I both grew up with cameras that had film in it.
Yes, we did.
Actual film canisters. And I remember traveling and being like, oh my gosh, you can't put the film canisters through the x-ray machine in your luggage. You have to get these special envelopes. Anyways, I just want to say, for those of you who grew up with digital cameras, you might know about film and you might not. I just want to be like, I'm not trying to be condescending. I just want to be like, I think we just need to be clear, because we may have hit a point where some of our listeners don't have experience with film in cameras.
Yeah, that's very true.
So the film itself had to be really special. But it turns out that the camera had to be really special too. And part of the reason is because this isn't just a point and shoot, like snap a frame camera. This is a panoramic camera. A panoramic camera works a little bit differently than a regular camera. Matt, when you pull out your iPhone and you take a pano, because panorama has too many letters in it for your iPhone. When you take a pano, you hit go, and then you, as a physical human, take your camera and you move your camera across the scene that you're trying to take as a panorama, right? Which means you literally have moved your camera lens across what you want to take a picture of, which is distinctly different than when you just want to take a portrait of somebody. The challenge with the Corona camera is that it's inside a satellite in space. It's a whole problem with equal and opposite reactions. And if you remember that scene from Gravity with Sandra Bullock and the compressed gas that she uses to propel herself back to the spaceship, this is what we're talking about. Equal and opposite reactions are really dramatic. So to have a panoramic camera moving inside a satellite creates too many equal and opposite reactions. So in the first early designs of Corona, they created this counterbalance to balance out those equal and opposite reactions. It turned out the electronics and the mechanics and all of the weight that was involved in putting a counterbalance into the spacecraft was too complex. So what they did is they cut the camera in half, and they cut the camera in half from sort of the lighter front part of the camera where the lens was and the heavier back part of the camera. And the heavier back part of the camera was how they created a counterbalance, so that the front lighter part of the camera could swish back and forth like windshield wipers, and the back half of the camera acted like a counterbalance, which essentially meant that it was spinning 360 degrees, while the front half of the camera was just going back and forth, back and forth.
So the camera gets to be kind of its own counterbalance.
Exactly. So instead of building in a whole separate counterbalance, you're splitting out that heavier part of the camera, which is causing all the problems with the equal and opposite reactions, and you're using it as the counterbalance to make the physics work.
So then once you've got your pictures, your camera has taken the pictures of Soviet territory, now you have to get those pictures back to Earth, right? And so you have to develop a technology for safely taking the canister of film and leaving the spacecraft, coming back through the Earth's atmosphere, and then somehow retrieving it before it can, say, fall into enemy hands or get lost somewhere along the way.
This is such a cool process. And it's very cool in part because in some ways, very simple in design, and in other ways, really complex and detailed, and the training that the pilots have to go through. These pilots are incredibly talented. So the only pilots that were allowed to go catch these buckets of film, right? So each Corona satellite has a bucket. Inside the bucket is the film, and the bucket is its own little return space capsule that gets ejected from the satellite down through the Earth's atmosphere back to Earth. When they know these buckets are being ejected, there's a series of 5 airplanes and a couple of helicopters. This is a whole crew of aircraft going out to catch these buckets. To be a pilot in one of these aircraft, to go catch one of these buckets, you had to be like 99% successful in training activities just to be able to go fly and catch one of these buckets, because it was so important to catch one. So imagine, let's just say it looks like a bucket, because it's not a bucket, but it has its own like heat shield, parachute, this whole thing. And you have all of...
It's not a Home Depot bucket. It's like a fancy bucket.
It's a really fancy bucket with your film inside, protecting, there's a heat shield and everything, right? It's its own contained thing because you have to protect that film. When they know that there's a bucket coming down, they know approximately where, right? And they deploy this formation of aircraft. There's a whole military structure here that I'm not going to get into because I don't understand it. But, there's a leader. They determine which airplane is going to be the best poised to catch that bucket. Behind the airplane, when they know which airplane's going to catch it, they deploy a bunch of webbing. It's kind of like a lasso. And the idea is that airplane flies right over the bucket's parachute. And then that parachute gets entangled in the lasso that's trailing behind the airplane. And that lasso is really a winch. And then they winch it back into the aircraft. If they miss it, what happens then, Matt? Because I think I just explained how you actually catch the thing, which is crazy to watch. And I really encourage you to go look at the video because the airplane has to literally make contact with the parachute, fly over the parachute for the bucket so that it gets entangled into the lasso at the back.
Yeah.
They don't call it a lasso, by the way, guys. I'm calling it a lasso because it makes more sense to me.
Yeah, what you just described, that's all the responsibility of the Air Force. The Air Force is meant to catch the bucket and bring it back to the ground for analysis. But if they miss it, the Navy is there as well. And the Navy is prepared to then fish it out of the Pacific Ocean. And if the Navy isn't able to get it out of the ocean, if it can't be found, there is kind of a built-in self-destruct mechanism, which is that the Corona bucket has a salt plug, which is exactly what it sounds like, a plug made out of salt that dissolves in the water. The seawater comes in, it destroys the film, and nobody can tell what the U.S. has been looking at with the Corona satellite.
But Matt, what happens if it lands on land? I mean, obviously, the Earth is covered in 75% ocean. The chances of this thing landing in ocean is pretty good. But it's not impossible for it to have landed on land, right?
Yeah, and the answer was to provide a kind of incentive that might bring it back to the people who really wanted it not to fall into the wrong hands. So there are actually 2 known instances of a Corona capsule going astray. In 1959, one fell somewhere off the coast of Norway, and it might have been recovered, but we think it most likely sank. I wasn't involved, but, people involved say that it probably sank. And the other one was, 5 years later, 1964, one landed in Venezuela and was found by farmers. And it was kind of a big deal. They realized that maybe at that point they shouldn't be putting the word secret on these capsules so that people wouldn't know that what they had was top secret. So instead, they carried an offer of a reward that was printed in several languages if they returned the capsule intact to the United States. So that's that incentive I was talking about, right? Like, don't tell people what they have is top secret, but instead offer them a reward for its return, and maybe you'll get your top secret stuff.
So, Matt, at this stage in the process of Corona taking photos, sending the film down, the film getting captured, we still don't have pictures because we're just getting the film to Earth. It is an enormous effort. How do we get the pictures?
Yeah. Well, my parents used to go to the photomat, right, and get their photos developed after they would take photos on the family vacation or whatever. In this case, there was a photo lab in upstate New York where they would develop the top secret photos, and then the photos were delivered to Washington, D.C., to whichever stakeholders had requested the imagery in the first place. And then they were analyzed, and the intelligence was shared with whatever agencies had a stake in the operation. As you can see, there's a lot of moving parts to everything, with the capsule coming down, being caught, being delivered to the lab, then being delivered to DC. And in its early days, this took a matter of weeks for all of this to get done. But by the end of the Corona program, it only was taking a matter of days. So, the process, the machinery around it, the human machinery included, kind of got more efficient over time.
And I think it's also worth noting that we're not talking about a single roll of film with 24 images on it. These rolls of film had an enormous amount of data contained on them.
And just in case you've got in your mind that this is a little roll of Kodak film like what you would pop into your camera at home, no, this is a very large reel of film, kind of similar to the reels of Hollywood movie films that you sometimes see in the archives, right? It's a big film reel. It's not like a little, film capsule. When we say capsule, maybe that's a little misleading.
I think that's where bucket helps. It's a bucket of film. It's not a capsule of film. Yeah.
It's a bucket, yeah.
Which were 2.5 feet across. And so when these airplanes were trying to capture them, it wasn't a teeny tiny like pill. It was like a mega bucket. If we're using bucket as a size, as a geologist, I'm like, it's more like boulder than cobble.
Yeah. What's the grain size of that rock?
Once the first successful Corona mission, aka Discoverer 14, returned one single roll of its special fancy space film. It was returned in 1960. The U.S. had gathered more intelligence on that roll of film, more images, than the entirety of the U-2 program at that point.
So that gives you an idea of the scale of going from scarcity to what seemed like abundance at the time. Through today's lens, that's different, right? So the intelligence community had to have a culture shift. It had to create workflows to manage those data in individual stovepipes. But then there had to be connecting horizontal pipes that brought all this together. My earlier exemplar of, I think I understand radars from this area to be associated with air defense systems. Corona, what do you see? What do you see, fellow imagery analyst? Well, I see an air defense system at the same place you believe you've seen air defense radars. Let's see how often those two specific images and those specific radars are at the same place and where they are. And then we can start to understand what specific radars they are, what specific types of missiles they support. So yes, I think the idea of scarcity to abundance, being able to take uncertainty. For instance, I think we estimated around that time that there were 140 to 200 ballistic missiles that the Soviets had. And when we got Corona and Grab up there, we then understood it to be 10 to 20, right? So the missile gap understanding went from assumptions to factually backed estimations for things like national intelligence estimates.
So the Corona program ran from the 1960s to the 1970s, and the images started getting declassified in the 1990s. And that's when we really understood how valuable those images were for scientific purposes beyond their initial use in the intelligence community.
It does sit in archives for historians. There was one wonderful use case where a great deal of formerly classified imagery from space systems, specifically declassified and made available to scientists studying the environment, and specifically what was going on with the polar ice caps, what was going on with glaciers. It's called the Global Fiducials Program. So the idea was, hey, we've got all this stuff. We've declassified the program. So those what we call the fact of. As time moves, we have no problem describing even in detail how Corona did its thing, because we're not worried about anybody copying it and using it against us, for instance. But when that imagery is declassified and used for myriad other purposes, it's a wonderful sort of cherry on top, right? That this imagery that was so and signals intelligence so critically important during the Cold War and the times following, that now, having chronicled the Earth over time while it was doing intelligence work, and that historical record is critically important alongside unclassified systems like the Landsat program, right, which has been providing continuous data for decades. So it is a wonderful resource for uses far broader than what they were originally intended.
The Corona program, I feel like, still lives on, even though we're not using this technology. We're not using the Corona program, or AKA the Discoverer program, anymore. But scientifically, the images that were collected by Corona are incredibly valuable and are still being used today to do a lot of tracking of glacier retreat, ice melting, and identifying archaeological sites and helping with archaeological studies. Because essentially, Us scientists now have these time capsules that allow us to go back in time and see parts of the Earth in ways that we never would have been able to see in the 1950s. And because it's no longer the 1950s and we don't have any time machines declassified yet, we can't go back in time and look at these places. And so this data that was collected for intelligence purposes has been declassified and is continuing to give back to the scientific community in huge ways.
And both Grab and Corona, just because those programs cease to exist, doesn't mean that we haven't continued to do things that are essentially the same, but with new technologies. Both of these programs were replaced by more technologically advanced satellites, and their legacies have rippled into intelligence and science communities still today.
AirSpace is from the National Air and Space Museum. It's produced by Jennifer Weingart and mixed by Tarek Fouda. AirSpace is hosted by Dr. Matt Schindel and me, Dr. Emily Martin. Our managing producer is Erica Novak. Our production coordinator is Joe Gurr. Our social media manager is Amy Stom. A big thank you to our guests in this episode, Andrew Ross from the National Air and Space Museum, and intelligence expert and historian Keith Masback. Additional thanks to the International Spy Museum for connecting us with Keith. Did you know that transcripts of our episodes include citations and extra fun facts? You can find them linked in the show notes, along with the sign up for our super fun monthly newsletter. For additional content, photos, and more, follow AirSpace Pod on Instagram and X. We're also on YouTube Shorts. Check us out on the museum's page. AirSpace is sponsored by Lockheed Martin and distributed by PRX.